Hello and welcome to this lecture on Laplace transform. So, in this video, we are going to see some problems and properties regarding inverse Laplace transform. So, these are some standard formulas. Already, we have studied these type of formulas while studying in the Laplace transform. So, just we know that a Laplace transform of e power at, it will be 1 by s minus a. Here it will be in the reverse manner. That's all. We know that Laplace transform of sin at will be a by s square plus a square. Cos at will be s by s square plus a square. As same as it will be in the reverse manner. If I am asking for Laplace inverse Laplace of cos at, then we have to say that is s by s square plus a square. If it is of Laplace inverse of sine sine h of at hyperbolic function, then we have to say that is a by s square minus a square. As same some other standard formulas, the Laplace inverse of 1, it will be 1 by s. Already we know that Laplace of 1 will be 1 by s. Then Laplace inverse of t power 1, it will be 1 by s square. As same as the similar problem. These are some new formulas and some other. We already know that Laplace of t power n will be n factorial by s power n plus 1. So here we know that Laplace, if I am taking the Laplace inverse of these terms, it will be the t power n. If I am asking for inverse Laplace of it will be t power n. So by using these formulas, we are going to solve the problem. The first problem, find the Laplace inverse of s by s plus 2 whole square. So here simply I am taking the numerator and I am making a sum rewriting the given function. Here it is, yes, I may add of s plus a. So it will match with e power minus at. Then we know that the Laplace inverse of 1 by s plus a whole square, it will be t e power minus at. So s plus a, I may take a as 2. So if I may rewrite the given expression in this form, it will be more easier to use the Laplace inverse formula. So on the next step, I'm using the Laplace inverse of 1 by s plus a. It can be written as e power minus at. The Laplace inverse of 1 by s plus a whole square, it will be t e power minus at. So here a will be 2. Finally, here we can find the solution. It will be on the subtraction. So I may substitute the values. Instead of this, it will be e power minus at. Instead of this, here it will be t e power minus at. So here I may take this 2 as a constant outside. So I'm getting the 2 e power t power minus 2 t. So I'm going for the next problem. Next problem, here it will be Laplace inverse of 1 by s square plus 2s plus 5. A very easy problem. I'm just taking the denominator part because with this quadratic formula we can't apply the inverse Laplace. So I may rewrite this function as s plus 1 whole square plus 2 square. So if I expand this, how it will be? It will be of 1 plus 2s plus 4. So 1 plus 4, it will be 5. Again, I may get the same. So for our simplification purpose, I may rewrite like this. On the next step, here I may substitute this denominator part. After simplification, we have it some direct formula. Inverse Laplace of 1 by s plus a whole square plus b square, it will be e power minus at sin bt by b. So here b value will be 2 and a value will be 1. So by substituting this, I'm getting the final answer as e power minus t sin 2t by 2. The next problem. Here it will be of inverse Laplace of 1 by the same previously what we did. We used to simplify this term by using this. I'm just expanding this for your simplification. Then 6s plus 4. So here it will become 13. So similarly, I'm getting the same expression. I have rewritten this as like the previous term. We may substitute that, and using a similar formula, we may get e power minus at sine bt by b. Here b will be 2 and 3 will be a. So on substituting, I'm getting the final answer. Next, the similar problem. I'm equating this, and finally here if I use this term above the term, if you see the previous problem, there won't be anything. Here it will be of simply 1. But in this problem, I have given that yes. So within the yes, we can't apply any formula directly. So I am just taking that 2 minus 2. Then I may split these two terms. And now we can apply the first shifting theorem. First shifting theorem will be e power minus at f of t, while if it is in the Laplace inverse, already we have studied in the Laplace transform, e power f of t can be written as capital F of s. So here if I bring the Laplace to that side, it becomes Laplace inverse. So here it will be s plus a. So what it will be in the first shifting theorem, it will be of s plus a. So here minus na, that will be plus. So I'm taking the inverse to that side, Laplace to that side, it will be Laplace inverse. So this is what the first shifting theorem. By using this, I may rewrite that s plus 2 by s plus 2 whole square plus 1, it can be written as e power minus 2t. In the place of a, here we have 2. And we used to say that 2 by cos means s by s plus 1 whole square. So how it will be in this cos, the Laplace of cos t will be cos at will be s by s square plus a square. So here with this a will be 1, then there is a value s. After that we may substitute s equal to s plus 2 because we have the exponential e power minus 2. So a similar manner we are getting the sine. The Laplace of sine will be a by s square plus a square. So finally, on taking these terms, I'm getting this answer. The next problem, Laplace inverse of s plus 2 by s square plus 2s plus 2. I'm just taking the denominator part and I'm making a simplification. Next, I'm taking the numerator part. For my convenient, I'm taking that 2 as 1 plus 1 and I'm splitting out the terms similar manner, and I'm just applying the first shifting theorem. Whenever if you are getting the square with any of the term, we have to apply the shifting theorem. So this is also a first shifting theorem. By using this, we can rewrite this Laplace inverse of s plus 1 by s plus 1 whole square plus 1 can be written as e power minus t cos t. Here you have to remember that here it is of s, we will get cos. Here it is of a constant, here it will get sine. Finally, this will be the answer.